In this lecture, we will define the absolute positioning principle. So the absolute positioning uses the pseudo ranges. So, for example, your mobile phones or vehicle tracking systems use this mode of positioning. So these systems, the model for absolute positioning is a standalone model. This means that you track, or your device tracks, the satellites. So, and the data will be observed from the satellites. The distance will be measured using the pseudo-range measurement method, and then you can easily determine your position, so without using extra information. So now let's introduce the mathematical model for the absolute positioning. So the satellite positioning principle is well known by you. So we need to determine our receiver position in a geocentric coordinate system by making measurements to the satellites. And if we know the satellite's position, we can then, by using the measurements, we can obtain our receiver position in a three-dimensional coordinate system. So now we will write the model for our observation. So our observation model here includes the pseudo-range at the left-hand side, the measurements. We, at the receiver, measure the distance between the satellite and the receiver antenna. So this is included in pseudo-range measurements. And all measurements include the so-called random errors. So these random errors are also included at the left-hand side. So we talk about pseudo ranges because direct obtaining of the geometric distance between the satellite and the receiver is impossible due to several error sources. So that's why we should introduce the the systematic errors. For example, our first systematic error is the the receiver clock error, and the second one is the satellite clock error. And the next two errors stem from both the receiver and the satellite. So this type of error is called as hardware clock or hardware error. Or receiver hardware bias or clock hardware bias. So the signal travels through the atmosphere, and the first it penetrates into the ionosphere, the top level atmospheric layer, and then comes to the close to the Earth's surface, and it penetrates through the troposphere. So these two should also be included in our modeling. And the next one is the multipath, and the multipath modeling is not so easy. So that's why will be omitted in most of the standalone absolute positioning applications. So for our modeling, we will then only deal with the first three terms at the right-hand side, so namely the geometric distance between the receiver and the satellite, and the receiver clock error and the satellite clock error. The other, will not be modeled in our example, so that's why we omit those terms. But in practice, it is normally impossible to model this hardware bias, so these will be obtained from other sources. So or these errors will be included in the satellite and also in the receiver clock error. So that's why they will be omitted mostly. And the next two error sources, the ionospheric and tropospheric corrections, can be brought to the equation by using some certain models. So for example, for GPS, Klobuchar model is or can be used, or for tropospheres the same is true. Some models exist, and these models can be used for making the correction to the observations. So, but in our case, we will omit all these 5 terms here, and we will only deal with these, okay, the right-hand side of our equation. So the geometric distance is modeled, as you can see, the distance, the norm, the norm can be easily defined. So this is the difference between the satellite and the user's location in 3 terms. So if we take the norm, so we can easily compute the geometric distance, and the next 2 terms will be the receiver clock error here, the first one, and this is the satellite clock error. And as you recall, the satellite's position can be computed from the, in case of GPS, from the broadcast ephemeris, from the navigation message file by using Keplerian parameters. And the satellite clock error is also included in the GPS navigation file. So that's why we will not introduce this term, or the satellite clock term, clock error, as the error source, or as unknown. So our observation equation is here, as you see, and this observation equation does consist linear terms, like here. This term is linear, but so there are some terms. The norm equation includes nonlinear terms. That's why we must linearize our problem. So you already are familiar with the linearization in the 8th week of this lecture. So you are introduced to the linearization process on a terrestrial 2-dimensional distance measurement case. So we will then shortly or briefly describe how to linearize our equation. So the right-hand side, the first term, geometric distance, is denoted by rho ik here, and it is given by the norm. So if we would like to linearize this term, so we expand this term into Taylor series, and the terms, the nonlinear terms, the second, third, and fourth order terms will be skipped, will be omitted, and we only deal with the first order terms. These are the linear terms. So this means that we will take the derivative of the geometric distance here in terms of the x, y, and z component respectively. So now we can carry out our linearization if we take the derivative in terms of x, y, and z. So the linearization will look like the equation given here, and the rho will then be the distance, the geometric distance will be easily expressed in this equation, in this linear equation. If we put this geometric distance into our equation, and the unknown parameters will be left at the right hand side here, and the other parameters, the known parameters, will be brought to the left hand side. So then we can build our functional model. So as you recall here, this is the measured pseudo-range distance minus the geometric distance, and we also take this to the satellite clock error to the left hand side. So all known issues, all known components will be at the left hand side, as you see. And at the right hand side, so our satellite's position delta x, delta y, and delta z, plus the receiver's clock error is included. The 4 unknowns and their coefficients are at the right hand side. So why do we introduce the receiver clock error? Because satellites use perfect clocks, so atomic clocks. On the other hand, the receivers use lower price. Receivers use clocks having a lower price, so the so-called quartz clocks. So that's why we want to also model the satellite clock error, and we would like to estimate the satellite, the receiver's clock error. And in this way, we can introduce the receiver's clock error as unknown. We can estimate from our observations. So as you also are aware of the linear equation, which is already introduced, so the linearization will then be expressed in a model. So you see the left hand side includes the lowercase l plus v is the error term, and at the right hand side, a is the coefficient matrix. So for example, these numbers, these 3 numbers for the delta x, delta y, and delta z components are the one of the or the 3 of the coefficients, and plus the coefficient, one more coefficient comes from this here, and this will then be a matrix having n times the observation. So how many observations, how many satellites are available in the sky, and how many satellites will be locked by the receiver. So will be denoted by n. For example, for our example, in the next video, we will introduce 12 GPS satellites, so that at the same time we observe 12, or we track 12 GPS satellites at a certain time, and the number of unknowns then will be 4, because three position or the Cartesian unknowns, so Cartesian coordinate unknowns, x, y, and z components, and plus the receiver clock error, so 4 unknowns. And this means that if we have at least 4 observations, we can solve our problem. So, but this definition will be a unique one, so that there will be no quality control. But if we will have more than 4 observations, we can control our observations. We can acquire some statistical measures by using the observations. Now, in the next video, we will realize the absolute positioning principle on a numerical example in Octave platform.